And now another Tales from the Graph. This tale has a lot to tell, and it's really important that we pay attention to what's going to be on the horizontal and vertical axes of the graphs to make sure we understand the whole tale. This is going to be our first look at bifurcations. We've talked about bifurcations before. Remember that a bifurcation is a qualitative change in behavior. And so by qualitative, we mean the quality of a dynamical system, such as how many equilibrium points it has and what kind of stability those equilibria have. So whenever that situation changes, like we get a different number of equilibria or the equilibria have a different stability situation, that's what we would call a bifurcation because it represents a significant qualitative change in the way that the system's going to operate. So the first bifurcation we're going to look at is a transcritical bifurcation, in which two equilibrium points merge, they become one, and they trade stabilities on either side of the bifurcating point. Let's stick with the Allee model. People really enjoy this model, and it has a lot to do with ecology. So let's just take a look. Recall that the Allee model looks like this in a graph of x versus x prime. So remember that right here we're looking at the rate equation, which is described by this polynomial form here. And that rate equation has three roots. So we have three equilibrium points. There's one at 0, there's one at A, and there's one at the carrying capacity K. So we've gone through this model quite a bit, and hopefully you're pretty comfortable with describing it and describing the equilibria and the stability. What I want to do now is I want to consider what this model looks like when A is less than K. When A equals K, that's where the transcritical bifurcation is going to occur, and then what it looks like on the other side when A is greater than K. So notice that in this video, I'm going to be considering how this function f of x changes as I play with the value of the parameter K. And for that, I'd like to introduce a fun new kind of diagram. This is a really amazing kind of diagram that describes a whole bunch of dynamics all at the same time. Remember when I said it's really important to pay attention to what's on the axes? On a bifurcation diagram, what we're going to do for this one-dimensional system is we're going to draw phase lines. So we're going to try to describe where the equilibria are and what their stability is for different values of K. And we're going to draw each of the phase lines here in a vertical fashion. And what we're going to do is we're just going to graph the equilibrium points only. Like on a usual phase line, we kind of draw the whole axis. Here it's a horizontal, but over here it's going to be a vertical axis. But for a bifurcation diagram, we're actually just going to draw the equilibrium points that we often call x star. And that's going to be on the y-axis. And then on the horizontal axis, we're going to illustrate how those phase lines change as we change a parameter of interest. So this type of bifurcation diagram is going to look different depending on what model you have and depending on what parameter you decide to alter. But for us, we're going to play with the parameter A and see how this type of bifurcation occurs when A is equal to K. Okay, so let's get started. And it all starts with just starting where we were before, understanding the Allee effect model. And we're going to pinpoint the equilibrium points, and we're going to describe their stability, and we're going to put that on this bifurcation diagram. Okay, so we have three equilibrium points there. Two of them are stable, and one is unstable. So for this, color coding is going to be really handy. So I'm going to label the unstable point at A, unstable in red. And then I'm going to label the two stable equilibrium points in blue. And so this one's stable, and the one at 0 is also stable. Okay? We've talked about this situation before, but now we're going to see how it changes as we vary the parameter A. That's what we have the bifurcation diagram for. So since I'm starting right here with some sort of situation where A is less than K, to get myself situated on the bifurcation diagram, I'm just going to tick mark off the place where A would be equal to K, okay, so that I know that for the phase line I'm going to describe here, I'm going to be in this area over here where A is less than K, okay. A looks like it's significantly less than K, so I'm going to draw the situation from over here from over there right here on the bifurcation diagram, okay? And it looks like we have one fixed point at 0, right? And then we have another stable fixed point up here at k. And remember that that value of k would be up here on the diagram. And then we have the unstable point, which is located at A. And so this is a little confusing. The values of A and K have meaning both on the horizontal and on the vertical axes here, because you can see that the fixed points are literally occurring at A and K. And so those are places that are going to be labeled here too. Just know that I'm just talking about graphing the equilibrium points only on the y-axis here. So there's one at A, and then there's one up here at K. Okay, now let's see what happens as I start to increase the parameter A. I'm going to keep it less than K, but I'm going to start to scooch the A a little bit bigger. So A is going to get a little bit closer to K, and then I'm going to redraw this picture. Then after looking at this picture, I'm going to relabel just the equilibrium points on this bifurcation diagram. Okay? And so, let's see. It's still going to go through 0, 0, but like I was saying, I'm going to take this A right here, and I'm just going to scooch it a little bit closer to K. So instead of A being over here, let's say A occurred over there. I mean, it would still look pretty much the same. And this gets to the part where I'm talking about qualitatively different or similar behaviors. If I move the A a little bit closer to K, I still have 3 fixed points. They still occur at 0, A, and K, and A is still the unstable one in the middle. The only thing is the A moved a little bit closer to the K, right? So this situation still falls under the category of A is less than K, except it's a little bit closer to K, so I'll probably draw it right here instead. And the A moved a little bit greater, so I'm going to put the red dot right there. The blue fixed point or equilibrium point at 0 stayed the same, so I'm going to keep that right where it was. And the other blue equilibrium point at K also stayed the same, and so I'm just going to keep that where it was. You see, really what's going on here is I'm drawing one phase line for the first value of A that I talked about. Then I'm drawing another phase line for the second value of A that I talked about. And now I'm going to, dare I say it, try to look at what it looks like when A is exactly equal to K. And I'm going to see that what's happening with these two fixed points, these two equilibria, is as I increase A is getting closer and closer and closer to K. And you see the red dot is going to move up and it's going to merge with the blue dot right there. Then instead of 3 fixed points, there will only be 2. And that is a different quality. So it's a qualitative change. That's where the transcritical bifurcation occurs. Okay, so let's erase what we did here. And now let's talk about when A is exactly equal to K. Okay, and this is going to be the bifurcation point. So remember, here's where the A was. And now I've scooched it closer and closer and closer to the K. And this is the case where it's literally equal to the K. Okay? What happens when A is actually equal to the K is that we're going to have a double root here in this polynomial. And so we're going to have, our polynomial is going to look like that. It's going to be negatively valued, and then it's going to sneak up, and it's just going to graze the x-axis there, and it's going to be a double root, so that when it comes back down, it's going to still be negative. Okay? How that looks on the diagram, geez, well now I have a node. Remember we talked about nodes? Those are like really special cases. They don't often happen in real life. But at a node, what it's going to look like for the phase line is it's going to look negative here, right? Because we're tending towards the carrying capacity K from this direction. But in this zone, it's also negative, and really there's nowhere for it to go except to 0. So one thing that changes, there's no strictly unstable fixed point at K because there's no distinct value for K. K is the same, for A. A is the same thing as K now. So I have to erase that distinct unstable fixed point there. And then the other thing is that the thing that used to be stable about the carrying capacity is now kind of half stable, half unstable. So maybe I can draw it as like half a blue dot and half a red dot here, because it's kind of like unstable from this side, right? But it's stable from the other side. So I'm not trying to draw two dots. I'm trying to draw one dot with two different colors. This fixed point right here is now a node, right? It's half stable and half unstable. So it's a node. Half stable and it's half unstable. From what we were talking about with basins of attraction, this is the special case where you have an equilibrium point that is not fully stable, but it's not fully unstable. And so it actually does have an interval basin of attraction. All initial conditions over here will be attracted towards it, but then it also has like things getting repelled away from it. And so that's a mix of stability and instability. Actually, when I look at the bifurcation diagram, that kind of does make a lot of sense, because what I'm talking about is that, really, to follow my logic this whole time, I've been linearly increasing the value of A this whole time until this point right here, where I got the half and half. You see, this is a half and half. This is just one fixed point right here, one equilibrium point, a node at A is equal to K. Well, that's totally different than what I had before, because I used to have 3. You see, for all of these values over here, whenever A was less than K, I had 3 equilibrium points, right? But when I have A is equal to K here, actually I have that one equilibrium point there, which is half stable, half unstable. Do I still have my 0 point? Okay, yeah, I still have the point at 0 because that 0 root is occurring due to this term here. And you see, I'm not really messing with this term. I'm kind of just messing with this one over here. So I still have that 0 point being the same as it ever was. And so really what I have is I have this one equilibrium point here, a node at A is equal to K, plus I have this same equilibrium point here at X equals 0. And so really what's happening in this situation here is when A is equal to K, I have 2 equilibrium points. When A is less than K, I have 3 equilibrium points. When A is equal to K, I have 2 equilibrium points. So what's going to happen when A is greater than K? Now let's take a look and let's tell A to move a little bit more over here, and we'll see what happens when A is greater than K, and that will complete our big picture of a bifurcation diagram describing this transcritical bifurcation. Okay, so here's our final case here, where I'm going to keep K just where it was right there, but now I'm going to move A to the other side, because now A is going to be even bigger than K. Getting kind of messy on my board here. Right, K is still right here where it ever was, and that's still going to be an equilibrium point, but what happens is when A is greater than K, you see, A is now greater than K, so it's to the right of K. Now the polynomial looks like that. Okay, now I have to reassess the whole situation. Good thing I'm super comfortable with linear stability theory and how to draw a phase line on one of these x prime versus x graphs, so I can quickly pick out the stable point that's still there, the stable equilibrium at 0. Doing a quick in your head linear stability theory by kind of thinking of what the tangent line to this graph is and what the slope of the tangent line is at this root K. What is the stability now for the carrying capacity K? You see the tangent line there kind of has a positive slope to it, and so that means it's going to be unstable. So now K is changing from stable to an unstable equilibrium point. And likewise, going through the linear stability analysis for A leads me to visualize a tangent line with a negative slope. And so what happens is that A over here is now a stable equilibrium point. transcritical bifurcation, in which two equilibrium points become one. And then on the other side, they trade stabilities. Okay? I guess for the rest of this, since I'm going to make A so big, I'm going to have to erase the words up here so I can give it space. Now we're going to see the rest of the transcritical bifurcation taking place. As we increase A even more, now we're on this part. You see, on this part of the bifurcation diagram, the value of A is greater than the fixed value of K. This value of the carrying capacity, we are not manipulating that at all. Okay? So over here, I'll just give us a little more room on the vertical axis because now we're at a point where A is greater than K. You see, A is moving. So sorry for the confusion. Before A was there, and then A was here, and now A is all the way up here, is to the right of K, and sure enough, it has traded stabilities with K. So when we're in this situation over here, now A is the stable equilibrium point. Now K is the unstable equilibrium point. And now 0 is still, as it ever was, the stable equilibrium point at 0. So we didn't mess with that one at all. But kind of connecting the lines here, it seems like now this is the stable equilibrium point of A. See, A used to be an unstable equilibrium point. Now it's a stable equilibrium point. And over here, K, which used to be a stable point, has now traded its stability with A to be an unstable point. And 0, same as it ever was. 0 is still an equilibrium point this whole time. Maybe I'll kind of give it its own line just to illustrate what I mean. I mean for this dotted line to describing the stable equilibrium point at extinction is always remaining the same as 0, but what we have is a flip-flop, right? Right at the point where A is equal to K, we have a switch where carrying capacity used to be stable, but now the carrying capacity, which is the same, is now the unstable equilibrium, and A is the stable one. Keep in mind that this whole time, and this is always true in one-dimensional continuous time dynamics, is that if you have multiple equilibria on a one-dimensional state space, any stable equilibrium must be separated by an unstable equilibrium. There's no way on a bifurcation diagram for me to have two blue lines next to each other without a red line in the middle. And so it kind of makes sense that we've gone through this transcritical bifurcation and the stabilities had to get traded of the equilibria because I wouldn't be able to have a blue one. Remember, this one used to be blue? I wouldn't be able to have this one stay blue and this one also be blue without a red one in between. Okay, for any fixed value of A, which would be represented by a vertical line cutting into this bifurcation diagram, for any fixed value of A, it has to go blue, red, blue. It can't go blue, blue. It can't go red, red. So over here too, it has to go blue, red, blue. Okay, so there you go. That's what a transcritical bifurcation looks like. I'll just label it right here for good measure. This is where we get the transcritical bifurcation at the value of A exactly equal to K. And on this side of the line, just like on that side of the line, we had three equilibria. On this side of the line, we also have three equilibrium points. It's just that they've traded their stabilities, okay? So on this side of the line, when A is greater than K, A is the stable equilibrium point and K is unstable. On that side of the line. On this side of the line over here, I'll write it over here, when A is less than K, what we have is A is unstable. Actually, I'll write it the other way. K is stable and A is unstable because the K comes first when A is greater than K. So on this side of the line over here, K is stable. That way it lines up with just what I'm saying. You see the K is stable there. and A is unstable, because you can see in this whole region where A is less than K is stable and A is unstable. Bifurcations occur when there's qualitative different dynamics. And here, the qualitative difference here is that there's only 2 equilibrium points at this transcritical bifurcation, where there used to be 3, it turned into 2, and then it turned into 3 again, and when it went back to 3, they switched their stabilities. As interesting as the transcritical bifurcation is mathematically, I will say that I am not super thrilled about going through this and trying to describe it in context of the ecological model for the Allee effect, because when I was reading the ecology textbook, it describes the Allee effect and the Allee threshold A as the value of the population such that below that level, the population is so underpopulated that they have trouble staying alive. Like maybe it's a very social type of creature where it needs like a whole village to raise its children. If it's a low population, they can't find each other to mate, or they're not able to protect their clan. So everything in the ecology book always describes A as less than K. Now, I know some people out there studying ecology. Do you think it would ever make sense for A to be greater than K? Like, I don't know, because K is the carrying capacity, right? That's how much the environment can support of that population. And then A is supposed to be some lower level underneath which the population is not able to survive. And so for this, I hope nobody gets too mad, but I will say that this is not ecologically reasonable. Reasonable, I don't know how to spell that, to consider A is greater than K, right? Because A is supposed to be some low threshold and K is supposed to be the carrying capacity. Well, I just wanted you to keep that in mind. I don't know if you noticed that too, but it's still a nice illustration of transcritical bifurcations.